Welcome to Discrete Mathematics. If this would be your first time encountering the subject, you will probably find discrete mathematics quite different from other mathematics subjects. You might not even know what discrete mathematics is. So, hopefully, in this discussion, in this subject, you will shed some lights on what the subject is about and what you can expect as we move forward in our discussion. So, uh, if we are going to refer to dictionary, when we say discrete, it means individually separate and distinct, and then and that's an adjective. So in other words, when we say discrete, it is separate, it is detached, distinct, and abstract. So defining discrete mathematics is hard because defining mathematics is also hard. So when we say what is mathematics, uh, in algebra or calculus class, you might have found a particular set of numbers. You would represent this set as interval. Okay, for example, the half interval of 0 to positive infinity, okay, is the range of the function of x, where the function is x squared. Since the set of outputs of the function are all real numbers, 0 and greater than 0. So this set of numbers is not discrete. The numbers in the set are not separated by much at all. In fact, take any two numbers in the set, and there are infinitely many more between with them, okay, which are also in the set. So discrete math could still ask about the range of a function, but the set would not be an interval. In other words, it is difficult to define discrete math because it is very broad. It has very broad description, which encapsulate a large number of subject. So in this subject, we will study four main topics. These are the combinatorics, the sequences, symbolic logic, and graph theory. However, there are other topics that belong under the discrete umbrella, which includes computer science, abstract algebra, number theory, game theory, probability, and geometry. Okay, and then some of these, particularly the last two, have both discrete and non-discrete variants. So ultimately, the best way to learn what discrete mathematics is to do it. Okay, so let's start the discrete mathematics. So let's have the foundation, logic, and proof. Okay, so let's start with the um, propositional logic. So um, um, the rules of logic gives precise meaning to mathematical statements. These rules are used to distinguish between valid and invalid mathematical arguments. So, because a major goal of this discussion is how to understand and how to construct correct mathematical arguments, we begin our discussion of discrete mathematics with introduction to logic. Besides the importance of logic in understanding the mathematical reasoning, logic has numerous applications to computer science. So these rules are used to design a computer circuit, the construction of computer programs, the verification of the correctness of the program, and in many other ways. Okay. Furthermore, software systems have been developed for constructing sometime, but not all, okay, types of proofs automatically. So later on, we are going to discuss these applications of logic, okay, in the later portion. So to start, let's have proposition. Okay, so in our discussion, we begin with an introduction to the basic building blocks of logic, which is the preposition. So, a preposition is a declarative sentence, that is a sentence that declares a fact that is either true or false, but not both. Okay, so that's what do we mean by preposition. For example, okay, let's have this statement. Washington D.C. is the capital of United States of America. So this is, of course, a statement which presents facts. So this can be answered by a true or false. So this is since this is a statement which involves a true statement, then this is a proposition. Another, we have Toronto is the capital of Canada, and 1 plus 1 equals 2. Okay, these are proposition statement because, of course, this can be supported with facts, and then we could also answer this one by a true or false. Another, we have 2 plus 2 equals 3. Still, this is a proposition, although that this is a false statement. Okay, so since you have uh, these statements can be answered by true or false, but never be both true and false. So therefore, this is a proposition. Okay, another, let's have this statement. What time is it? Okay, so in this case, this is not a proposition because it is not a declarative sentence. Another, okay, read this carefully. Okay, this is also not a proposition because this cannot be answered by a true or false. Okay, another, we have x plus 1 equals 2, and uh, x plus 1 equals 2. So this statement is also not a proposition because this statement is either true nor false. Okay. Note that in the first in the sentences in the sentence 3, okay, we can turn this into proposition if we assign values to the variable. Okay, so in other words, since the x here has no variable and has no value at all, then this is not a proposition. Okay, this will become a proposition if there is now a value in our variable. um, we use letters to denote propositional variables or statement variables. That is variable that present proposition. Okay, just like uh, letters that are used to denote numerical variable. Okay, so the conventional letters used for the propositional variables are P, Q, R, and S. These are conventional. So the truth value of a proposition is true will be denoted by a capital letter T. Okay, if the proposition is true, and the truth value of a proposition is false, which is denoted by capital letter F, if it is a false proposition. So the area of logic that deals with proposition is called propositional calculus or uh, propositional logic, which this was then first developed by a Greek philosopher, Aristotle, okay, more than 2,300 years ago. Okay, so uh, we but these methods were discussed by this was then there is a new uh, methods of or there are new propositions that in in the latter years. So these methods were discussed by English mathematician uh, George Boyle in 1854. Okay. Many mathematical statements are constructed by combining one or more proposition. So this new proposition is called compound proposition. Okay, so let's have this one. Uh, Now let's have negation. Okay, so negation, let P be a proposition. The negation of P, okay, which is denoted by that symbol, okay, so this symbol, okay, we have this one, okay, also denoted by another, which is this one, is a statement, okay, this can be read as it is not the case that P, okay, the proposition negation of P, okay, can also be read as not P. The truth value of the negation of P, which is can be read as not P, is the opposite of the truth value of P. So this would be the truth table. So if the statement is true, then the negation of that statement is false. If the proposition is false, then the negation of that one is true. Okay, let's have example. Find the negation of the proposition Michael's PC runs Linux and express this in simple English. So if this would be the statement, then we could have it is not the case that Michael's PC runs Linux. So we could have this one. So we have it is not the case that Michael's PC runs Linux. So that would be the negation. Okay. But uh, we can have a simpler statement which has the same meaning. We could have Michael's PC does not run Linux. Okay. So these two statements are the same. Okay. However, the second statement it's much more simpler, okay, as compared to the first statement. However, still these two statements are the negation of the proposition Michael's PC runs Linux. So let's have some other logical operators, okay, that use to form a new proposition from two or more existing proposition. So which this is also called connectives. So let's have conjunction. So let P and Q be proposition. The conjunction of P and Q denoted by P with this symbol, okay, which is can be read as P and Q. The conjunction P and Q is true when both P and Q are true and is false otherwise. Okay, so this would be the truth table of the conjunction, okay, of two propositions. So if P is true and Q is true, then okay, the P and Q, okay, is true. Okay, if P is true and F is false, then P and Q are false. Okay, if you have P which is false and Q is true, then still it's a false. And if both P and Q are false, then they are false. Okay, so let's have an example. Find the conjunction of the proposition P and Q, where P is the proposition Rebecca's PC has more than 16 gig free hard disk space, and Q is the proposition the processor of Rebecca's PC runs faster than 1 gigahertz. So for our solution, the conjunction of the proposition P and Q is the proposition we have Rebecca's PC. Rebecca's PC has more than 16 gig, has more than 16 gig free hard disk space. And, okay, comma, and the processor, okay, of the processor in Rebecca's PC runs faster. Okay, and okay, the processor in Rebecca's PC runs faster than 1 gigahertz. Okay. Uh, this conjunction can be expressed more simply as we could have Rebecca's PC has more than 16 gig free hard disk space, and its processor runs faster than 1 gigahertz. So we could have the simpler one. We have Rebecca's PC. Re- you have Rebecca's PC. Okay, runs faster. Okay, than ran fast. Rebecca's PC ran has more than, rather wrong, has more than, okay, has more than 16 gig free hard disk space, and its processor runs faster than 1 gigahertz. Okay, period. So this is much more simpler. The Rebecca's PC has more than 16 gig free hard disk space, and its processor runs faster uh, than 1 gigahertz. There must be done here. So these two statements are the same. There is a conjunction of two propositional. Okay, so let's have another. So we have this junction. So let P and Q be propositions. The disjunction of P and Q denoted by this one, which is can be read as P or Q. The disjunction P or Q is false when both P and Q are false and is true otherwise. So this would be the truth table for the disjunction of two propositions. So you have there, if P is T or true and Q is true, so you have P or Q is also true. When P is true but Q is false, then P or Q true. Then you have if the P is true, then if P is true false and Q is true, then P or Q is true. And if both statements or both propositions are false, then P or Q is also false. Okay, so let's have this one. The use of the connective or in a disjunction corresponds to more than two ways the word or is used in English. Namely, we have this one. So we have inclusive or. So a disjunction is true when at least one of the two proposition is true. Okay, for instance, the inclusive or is being used in this statement. Students who have taken calculus or computer science can take this class. So here we mean that the students who have taken both calculus and computer science can take the class, as well as the students who have taken only one of the two subjects. Okay. In other hand, we also have the exclusive or. Okay, when we have, for example, we have this statement: students who have taken calculus or computer science, but not both, can enroll in this class. So here we mean that students who have taken both calculus and computer science course cannot uh, take the class. Only those who have taken exactly one of the two courses can take the class. Okay. So what is this junction of the proposition P and Q, where P and Q are the same propositions as the previous example? Okay. So in the previous example, we have Rebecca's PC. Okay. You have Rebecca's PC. Okay, is more than uh, you have Rebecca's PC has more than 16 gig free hard disk space, and the Q, okay, proposition, the processor of the processor in Rebecca's PC runs faster than uh, 1 gigahertz. So in this example, okay, since it is disjunction, we could have Rebecca's PC has at least 16 gig free hard disk space, or the processor in Rebecca's PC runs faster than 1 gigahertz. Okay, not at least. Okay, more than. Okay. Well, anyway, at least and more than not, they are not synonymous. Uh, More than the P statement or P proposition is Rebecca's PC has more than 16 free hard disk space. So for our disjunction, we could have we have Rebecca's PC. uh, so the answer would be Rebecca's PC has more than 16 gig of free hard disk space, or the processor in Rebecca's PC runs faster than 1 gigahertz. So that's the answer to this example. Okay. So this would be, okay, as we can see here, this is the truth table for the exclusive or for two propositions. So you have here the symbol. Okay, as you can notice, the symbol for the exclusive or. So we have this symbol for our um, exclusive or. Okay, so you have there the truth table. If P and Q are both true, then P you have P or Q exclusive is false. So if one of the two propositions is false, then it is true. And if both proposition is false, then it is false. Okay, so let's have conditional statements. So let P and Q be propositions. The conditional statement P, okay, arrow Q, which can be read as if P, then Q. Okay, the conditional statement P, then Q is false when P is true and Q is false, and true otherwise. In the conditional statement P, then Q, P is called the hypothesis or antecedent or premise, and Q is called the conclusion or the consequence. So this would be the truth table for the conditional statement. So if both propositional statements is true, then you have P then Q is also true. If one of those statements is false, okay, if P is true and Q is false, then the truth table of the conditional statement P then Q is also false. If the P is false and Q is true, then it is true. And if both of them is false, then it is true. Okay. So the statement, okay, P then Q is called conditional statement because P then Q asserts that Q is true on the condition that P holds. So the conditional statement is also known as implication. So as you can see in the truth table, for the conditional statement P then Q, okay, note that the statement P then Q is true when both P and Q are true, and when P is false, okay, no matter what truth value Q has. Okay, so there are many uh, expressions of the conditional statement. You could have if P, then Q, or you could also have if P, Q, or P is sufficient for Q. You could also have Q if P, then Q when P. Okay, you could also have a necessary condition for P is Q. You could have Q unless negation of P. Then you could have P implies Q, or you could also have P only if Q. Okay, another statement could be a sufficient condition for Q is P, and then you could have Q whatever P, and you could also have Q is necessary for P, and Q follows from P. So all those statements, if that would be the way it was then said, it they are conditional